Let's talk about Chapter 4, Hazard Recognition. So there's two general categories of hazards we'll discuss. We have health hazards and physical hazards. The health hazards fall into two broad categories, the acute and then the chronic. Acute health hazards typically happen quickly. So if you spill hydrochloric acid, you're going to know about it because it's going to burn very, very quickly. If you breathe in asbestos, you're not going to feel the effects for a very long time. And you may never feel the effects if it's just, one time that you inhale it. It's the things that typically happen over time that lead to chronic health issues. Of the two, the acute are easier to deal with because people can recognize them and, it's just human nature. If there's a fire, to run, but you can't just sense asbestos dust in the air. So we have physical hazards, which consist of things like noise, vibration, extreme temperatures. So, a really hot factory or a really cold warehouse. Combustible liquids, compressed gases, explosives, and flammables. Now, there is a difference between a combustible material and a flammable material, and it has to do with something called the flash point. So the flash point is the lowest temperature at which vapors on the surface of it in a test will ignite and burn. What this means is that the lower the flash point is, the less likely something is to catch on fire. So if you have gasoline near a heat source, that heat source needs to get to a certain temperature to ignite the gasoline. Some things respond differently to heat sources. So if you have gasoline and diesel an equal distance away from a flame, and you steadily move that flame closer, the gasoline will catch on fire faster, right? It's got a lower flash point, more likely to catch on fire. So flammable materials have a flash point below 100 degrees Fahrenheit. So gasoline is an example of this, a highly flammable material. Combustible materials have a flash point above 100 degrees Fahrenheit. So diesel fuel or motor oil is an example of this. They will burn, but they do not catch fire as easily as gasoline does. So we have something called explosive limits that help us determine if an atmosphere is safe or not. Right? So if you have a gasoline refinery, there will be chemicals all over the place, including in the air. We have to have a measurement for how much dangerous flammable material is in the air at any given time. So we have two limits. We have the lower flammability limit, or the LEL, and the upper flammability limit, known as the UEL or UFL. The lower flammability limit is the minimum concentration of chemicals in or at above which the material will support combustion. The UFL, the upper flammability limit, is the highest concentration above which a material will not support combustion. So think about it like this. If you have a little lawnmower, it's got a carburetor. The carburetor combines gasoline and oxygen, feeds it into the cylinder. There's a little spark plug that makes a tiny explosion over and over and over again. So if there's not enough gasoline in every stroke, right? So the spark plug goes off, there's just air and a little bit of gasoline, you will not get combustion. This is an atmosphere that is below the lower flammability limit. There's not enough gasoline combined with the air to produce combustion. On the other hand, if the carburetor provides too much gasoline for the amount of air in the chamber, in the cylinder, you won't get combustion either. There's too much gasoline. So you can think about it, say you take a cigarette lighter and you dunk it in a can of gasoline and you try to light it, right? It won't do anything because it's essentially under the gasoline. There's no oxygen. There's no way to create combustion. So this has exceeded its upper flammability limit. So we use this information. They have LEL meters to determine if an area is safe for hot work. So generally under 10% flammability is good enough to do hot work, aka welding or cutting or grinding in a facility. The range between the LFL and the UFL is important. The wider the range, the more dangerous, more flammable, the bigger fire hazard an area is. You want that range to be narrow so there's less chance for combustion. Let's chat about the combustion triangle. So we need three things for combustion or fire. The first is heat or an ignition source, so a box of matches, right? The next is the fuel. So typically we'll just use gasoline as an example. To start a fire, you get a match, gasoline, fire. The third, something you might not think about as much, but you do need oxygen. So if you light some gasoline on fire, oxygen is coming from the air around you. Now, why I want to talk about the combustion triangle is to talk about other chemicals. So organic peroxides and oxidizers are chemicals that release oxygen when they're burned. So if you have a fire and you introduce more oxygen into that combustion cycle, you're going to get a more intense flame. So things like a turbocharger or a supercharger on an automobile or an airplane engine are doing this by compressing the air before it goes into the cylinder. So you're getting more air, aka more oxygen, and you can put more fuel in there to keep the right mixture, and it'll create more energy per cycle. So if you look on a hazard triangle, there is a symbol for things that are oxidizers that would create oxygen. Some of the common ones are chlorates, peroxides, perchlorates, and nitrates. Pyrophorics are chemicals that spontaneously ignite in air or temperatures of 130 degrees or less. So these are the reactive metals, usually on the far left of the periodic table. So sodium, lithium, and potassium. If you throw pure sodium into a pond of water, it will explode. Now, sodium can be mixed with chloride to make table salt, in which case it's totally inert. It becomes a compound at that point. But pure sodium, you really won't find it outside of a scientific laboratory because of the danger involved. Too much exposure to oxygen, and it can spontaneously ignite. The next term we want to know is specific gravity. Specific gravity is a comparison of a liquid or solid to water or a gas to air. So we're comparing the density of each. Water has a specific gravity of 1. So substances either have a specific gravity equal, less than, or greater than. If something is less dense than water, it will float on top of water. Something with a specific gravity of 0.5 will float on water. Most petrochemicals, so diesel or oil, do have a specific gravity less than water, so they will float. Substances with a specific gravity greater than 1 are heavier than water, so they will sink. This is mentioned in this particular textbook because of tanks. It's important to know what substance will go where when you're filling or flushing or changing the chemicals in tanks. If you know there's diesel and water in a tank and you know the specific gravity of those substances, you know where they're going to be. Just like a bottle of salad dressing, you can see the layers separate between the oils and the vinegars or whatever you put in there. Air has a specific gravity of 1. So we compare gases to air. If a gas has a specific gravity greater than 1, it will sink. So it will tend to hug the ground. Specific gravity, if the specific gravity is less than 1, it will float, right? So an example is methane or natural gas. Natural gas has a specific gravity of 0.554. This means that it floats away. So if you have a natural gas leak in your home, it's going to float to the ceiling, and if it can, it'll escape out a window. On the other hand, propane, a very similar chemical used for similar purposes, has a specific gravity of 1.552. This means it will sink. So if you have a propane leak in your home, it will fall to the floor or fill up your basement. So there's safety hazards associated with each for sure, although propane is typically considered the more dangerous because it tends to stay near the floor and fill from the bottom up. So just being able to look at a chemical MFTS sheet, spot that specific gravity, you know something about that chemical, about where it's going to be in its given environment. The next term is the term health hazard. A health hazard is a chemical with a scientific evidence showing acute or chronic health effects. These effects will be on the MFTS or SDS sheets for that particular chemical. If you're at work and you want to know if something is dangerous, it's required by law that you should get access to those data sheets to let you know what health effects could occur. The MFTS or SDS sheets also have recommended action, what kind of PPE type stuff you need, what types of dangers you are exposed to. Let's talk about the next batch of hazards. We have corrosives. Corrosives cause visible destruction or irreversible alterations in living tissue by chemical action. These can be either highly acidic substances or highly basic substances. So you can check the pH scale. The pH scale goes from 0 to 14, with 7 being neutral and 0 being acidic, 14 being basic. Any 0 and 14 are both extremely dangerous. Acids and bases are both very, very dangerous and corrosive. The next is an irritant. So you'll see this at the grocery store looking at cleaning chemicals. Irritants are not corrosive. They cause reversible inflammatory effects. So you might get a rash, but it will go away. It won't cause long-term damage like a corrosive substance will. So I want to emphasize this because the symbology looks kind of similar, corrosive and irritant, but they mean very, very different things. A sensitizer causes most people to have an allergic reaction. So a lot of chemicals you smell and you don't like, right? So ammonia or Clorox typically does not smell appealing to most people, and that's typically as close to as you get to that chemical. A neurotoxin is a poison that affects the nervous system. A mutagen can cause genetic damage, and a teratogen can cause adverse effects on a human fetus. So that's it for Chapter 4, Hazard Recognition. We're going to talk later in the semester in more detail about most of these categories and talk a little bit more about the MFTS and SDS labels, the symbology, what to look out for.